All right, we're going to work practice problem 6.49 from the end of the chapter. This one has to do with something called bomb calorimetry, which is also kind of a cool concept, okay? The reason why that's interesting is, you hear about food and the calorie content of food. Well, it turns out that we can measure the caloric content of foods in this way, using this device called a bomb calorimeter. Now, I drew a figure on the board. I'm going to explain it, but there's also a picture of this on page 272, which is a better figure from your textbook. You can take a look at that if you want to. I just have a simplified diagram, but it's going to be a calorimeter, which means we're going to measure heat flows. And the way that that's usually done is there's usually a large bucket or tub that would sit on a countertop, okay? And inside that, and this is all insulated, okay, from the outside world to keep the heat in and prevent any heat flow from coming into here, okay? But inside of that, we're going to have another chamber, a bucket filled up with water, and that's shown right here, okay? Could be some other fluid as well, but perhaps we'll just use water for our example. Now, we're going to take a thermometer, dip it down into that water so that we can measure the temperature before and after the experiment. And then what we're going to do is we're going to have an inside container that's sealed off from the water. Okay, this would be made out of metal. That's called the bomb. Okay, and what that is it's basically a chamber that we're going to put a sample that we want to test. And the way that this works is we always run a combustion reaction inside of the bomb. So before the experiment, we take this enclosure, this seal-off container, we put our sample in there. We also put a wire down in there with an electrical ignition system so that we can basically combust this later and push a button electrically from the outside world and get this to combust. But we also pressurize this bomb with oxygen gas prior to the experiment. And we purposely add enough oxygen gas or a high enough partial pressure of oxygen gas to assure that the oxygen is not the limiting reagent for our chemistry. In other words, the amount of sample will run out before the oxygen, because combustion reaction is the sample plus oxygen, right, to make products. So we assure that oxygen is not our limiting reagent, but the sample is, okay? And that's an important step experimentally, because what we want to do is measure the calorie content of the sample or the heat of combustion. We can only do that if the sample is our limiting reagent, so that's important. So we pressurize this with oxygen, we rig up this electrical ignition system, we put our sample in there, a fixed mass of our sample, we know how much sample is present, how many grams. We set up the whole apparatus, seal off that bomb, put it down in the water, let it come to thermal equilibrium, get the initial temperature before we light anything. Then, as soon as the temperature stabilizes, we get that initial temperature. We use our ignition system to light the stuff on fire, so to speak, or combust it in our oxygen atmosphere. It burns the sample up. This generates heat because these reactions are exothermic in nature. The heat which is generated inside of our bomb gets transferred out to the water because this is made out of metal, okay, a good conductor of heat. The water absorbs the heat energy from our reaction, our exothermic reaction. The temperature goes up, we measure that with our thermometer, and we can quantitate how much heat was released as a result. That's what this problem is all about. Okay? So let's take a look at what we're doing in the specifics. A 2.15 gram sample of glucose, which is a sugar, a carbohydrate, is placed in the bomb. That's going to be our sample. One more thing to take a look at here before we go on. You may have heard of this term before, carbohydrate. This is a good example of one, okay? Carbohydrate, the term's thrown around a lot. Chemically, you can recognize this by something that has this empirical formula, CH2O. The name is really synonymous, right? You think of carbon, carbo. Oops, I need to adjust my camera a little bit. We're talking about carbohydrates, right? You can recognize these by something that has an empirical formula, CH2O, carbohydrate, water, okay? Carbohydrate. If you reduce this down to the simplest formula, the empirical formula, it would be what? C1H12. H2O. Example of carbohydrates. Anyway, free information. Doesn't have much else to do with this problem about bomb calorimetry. But anyway, we take our sample of glucose, put it into our bomb. It's got a mass of 2.15 grams. Okay, we burn it or combust it in our bomb calorimeter. The calorimeter has a heat capacity of this. The calorimeter's temperature will then increase because it's an exothermic reaction from an initial temperature of 23, so TI 23.446 degrees centigrade, to a final temperature, TF, of 28.745 degrees centigrade. Notice how precisely we're able to measure our temperatures with this device. It's designed with that in mind, okay? What is the delta E, the change in internal energy, in kilojoule per mole units for the combustion of glucose? Okay? How many kilojoules per mole are given off when our glucose combusts in this oxygen atmosphere? All right. So boy, what are we going to do to figure this out? I've got a mass of my glucose sample that I used, and I know something about the temperature change. Okay. Well, a key equation to help us with all these calorimetry problems is to compute the Q, Q being the heat flow. Now that's always a change in temperature times something. Now the question, of course, is what is that something? Okay. Now in previous examples that you might have been following along with, okay, we multiply the specific heat of a substance times the mass of that material that's being heated or cooled times the temperature change. This is a little bit different. Okay. In this example, we're going to use a slightly different term, okay? This slightly different term is going to be called the heat capacity. Notice in the problem, we're given the heat capacity of our calorimeter. Now, what is this heat capacity, okay? Well, I think you might be able to best understand this by looking at the units on heat capacity. It's kilojoules per what? Degree Celsius or degree Kelvin. Okay? What this heat capacity tells us is how much energy in joules is required to raise the temperature of an object 1 degree centigrade or 1 degree Kelvin. How much energy is required to raise the temperature of an object 1 degrees centigrade? Now, what object are we talking about? Well, here it's our calorimeter. To find this number, you'd have to experimentally determine it through a separate experiment that you conducted in a sort of a control experiment. You would conduct it earlier on. Now, in this example problem, we're told what the heat capacity is, but if you're doing this in the lab, you'd actually have to measure it, okay, experimentally. But you know from previous experiments that to raise the temperature of our calorimeter 1 degree Celsius, it requires 6.317 kilojoules. Now this is different. This heat capacity is different from specific heat because specific heat talks specifically about raising the temperature of 1 gram of something 1 degree Celsius. Heat capacity, on the other hand, considers an object, a defined object, and it tells us how much energy is required to raise the temperature of the object or the device 1 degree Celsius. It's different, okay? It's a different name, a little bit different concept. And I want you to internalize heat capacity versus specific heat. It's not the same thing, okay? And so don't be tricked by that on homework problems or potentially on an exam. But if I multiply my change in temperature by my heat capacity for my calorimeter, I can figure out how many joules of heat energy are evolved, okay? So delta T is final minus initial, 28.745 minus 23.446. Both of those are degrees Celsius, so the units jive just fine. And if I do that computation, I learn that 33.4738 kilojoules of heat energy was required to heat up my calorimeter from 23.446 to 28.745, okay? So this is the heat that's evolved, basically, in this reaction with the combustion of glucose. A little over 33, well, a little under 33.5 kilojoules, okay? Got that? Makes sense, right? All right, now the thing is that I want to know what my internal energy change for my system is in kilojoules per mole. This is in kilojoules. It's the energy that was released, but it's not in kilojoules per mole because I haven't normalized it to number of moles of analyte that reacted, or number of moles of the substance that reacted, right? So I need to do that in a last step. Now, how do I do that? Well, I know in the problem I used 2.15 grams in this experiment. This is how much glucose I used. Now I'm going to assume that all that reacted because remember, I told you earlier that we do this experiment with excess oxygen. We always do it with excess oxygen. So the sample runs out first through a limiting reagent. And the purpose of that is that I can then take the mass of the substance that I burned and convert it into a mole quantity. And that's pretty easy to do. I just take the mass and divide it by the molar mass. Now, in the case of glucose, the molar mass is 180.156 grams per mole. Again, this is adding up all the parts from the periodic table of the elements. And if you do the math on that, you quickly figure out that you've got way less than 1 mole of glucose. In fact, you only have 0.011934 moles present in a little over 2 grams. Okay? So this quantity of heat was generated from reacting this number of moles. They scale with one another. If I increase the number of moles, I would increase the number of heat. Okay? So the amount of heat. So for this particular reaction then, this number of kilojoules is associated with this number of moles of glucose. If I change the identity of what I put as my sample, if I change this to something different besides glucose, the amount of heat would be different. It would not be conserved, okay? But for this particular substance, I can compute my delta E change in internal energy by taking my Q and dividing by my number of moles. I'm going to also make it negative because this is an exothermic reaction. The temperature rises as a result of the chemistry that occurs. Okay? So I'm going to do negative 33.4738 kilojoules was evolved when 0.011934 mole of the material reacted. Okay? And as a result, negative 2804.9 kilojoules per mole, or right around 2805 kilojoules per mole of heat energy is evolved when 1 mole of the glucose reacts in this experiment. Now, one more little detail here, okay? Notice that in this experiment, we were asked to compute what? Delta E, not delta H, okay? This is different than the example problem that we worked for the coffee cup calorimeter. Remember, we worked one of these as the last example problem for our coffee cup calorimeter. That was a benchtop device just made from a styrofoam coffee cup. In that case, it's open to the atmosphere, so the pressure is constant throughout the experiment. It's just the atmospheric pressure. This experiment is different because this bomb is sealed off. It's not open to the atmosphere. But the bomb is a consistent and constant volume. So there's no PV work done in this particular experiment essentially ever because the volume never changes. It's always the same. So the delta V is always 0. So because of that, there can be no PV work. All right? So as a consequence of that, what we're really measuring here is the change in internal energy for our system because the PV work is 0. and all of the heat energy, all the internal energy change and manifests itself as heat here, okay? So nonetheless, that's a bomb calorimetry experiment. I would rate this type of problem pretty important for this chapter. I'm going to guess you're going to see this in the homework. You could also potentially see this in the exam, just like you could with the coffee cup case, okay? So definitely know how to work this. It's a nice quantitative problem, and it's really interesting, right? Because you think about testing foods for their calorie content by this particular method, igniting it in the bomb, seeing how much the temperature increases, and relating that back to the calorie content. Now, in terms of food calories, glucose and sugar, our cells can use that. Notice that this is quite a high calorie content. This is a little over 2,800 kilojoules per mole. So keep that in mind when you drink that soft drink. When you're thirsty, you might want to get the diet version without so much sugar. Not that this is actually not the sugar that's in that. That's sucrose, but nonetheless, you get the idea, right? Watch those calories.